Most two-dimensional arrangements studied and computed to date are in the plane. However, we often need two-dimensional arrangements on curved surfaces. Consider, for example, Gaussian maps of polytopes, which in turn can be used to compute Minkowski sums of polytopes. Here's a short sequence from an earlier movie that shows how such Minkowski sums can be computed using 6 planar arrangements embedded on the 6 facets of a cube. While this technique proved to be efficient, it generated additional vertices on the boundaries of the facets, and it required identifying matching vertices on the boundaries of abutting facets. The 6 planar arrangements are induced by linear segments, which can be handled with rational arithmetic. Naturally, a rival technique that uses an arrangement embedded on the sphere, eliminating the additional boundary vertices, but still content with rational arithmetic, has good chances to surpass its competition. Another example that demonstrates the usefulness of arrangements on curved surfaces is the need to construct and maintain arrangements induced by the intersections of one surface with a collection of other surfaces. We developed a general framework for computing arrangements on two-dimensional parametric surfaces, which applies to a variety of topologies, including cylinder, torus, and sphere. It is based on the existing package that constructs and maintains planar arrangements. The domain is a rectangular two-dimensional parameter space with bottom, top, left, and right boundaries. An identification curve is a continuous curve, which is the mapping of opposite closed boundaries of the domain. A contraction point is a singular point, which is the mapping of a whole boundary of the domain. Code reuse is maximized by adapting the prevalent algorithms and their implementations, for example, efficient point location. The generalized code handles features embedded on a modified surface defined over a modified parameter space where the boundaries, identification curves, contraction points, and points at infinity are removed. Specific code that handles features that approach or reach the boundaries is added to yield a complete implementation. As we sweep over the surface in order to construct a data structure describing the arrangement of the curves, we have to take into account the topology of the surface. Although we removed the boundary of the parameter space, we now have to account for the fact that several arcs pass through the North Pole, which is a contraction point. When the sweep line reaches the end of the parameter space, we have to glue the arrangement features on the sweep line with their counterparts that were discovered at the very beginning of the sweep. Most of the machinery developed in Cgal for planar arrangements can now be used with arrangements on surfaces, provided that the user supplies the appropriate plugins for the specific topology of a surface and the geometry of the curves embedded on the surface. Here you see how two arrangements are overlaid on the sphere. The subdivision of the central sphere is the result of the overlay of other spherical arrangement around it. We can compute lower envelopes of surfaces over the sphere, which in turn we use to compute Voronoi diagrams on the sphere. Here you can see an example where the point sites are rendered in red and the diagram is rendered in blue. The bisector of 2 point sites is a geodesic arc. Here you can see an example of a power diagram on the sphere. In this case, the sites are circles rendered in red. The resulting diagrams are represented as arrangements and can be passed as input to consecutive operations supported by the arrangement package. Here you can see the overlay of an arrangement induced by the continents and the Voronoi diagram of the first 9 cities that hosted the Symposium of Computational Geometry in this millennium. More details can be found in the paper Sweeping and Maintaining Two-Dimensional Arrangement on Surfaces, a First Step, which was presented at ESA 2007, or in the following websites.